engage that much. Once again, a reminder, I am going to give an extension on the homework that I didn't put the Canvas reminder in. Merry freaking Christmas. You will have another, I guess another 2 days. You'll have until Wednesday night to finish the homework that was due on Sunday. There is no homework for Thanksgiving week, except for the people who are not listening. If you are not listening right now, you have extra homework, which is a special homework, which is for negative points. If you are not listening, please do that homework. It is hard and it will lower your grade. If you are listening, it is completely optional. I mean, you could turn it in if you want to lower your grade. I don't know, make it more challenging. Okay, but yeah. I think that's all the procedural announcements. No quiz again, no quiz this week. Thanksgiving, gives thanks. It's my least favorite holiday, so let's do something for it. Other administrative procedural questions? Anything about the class that's not physics? Okay, we've got Trace Diaz, 3 days left of Energy Land, 1 day for an entire review of everything. And then exam season, exam time, yay! Everybody loves finals. You guys are nervous as all get out. I'm nervous as all get out. I want you guys to succeed. I really do. My thought is I'm going to give it up to you. I'm going to let it be up to you. 1, 2, 3 days for energy review, 1 day for final exam review gives us the most time on the stuff that you know least, presumably. But if you so choose, I'm going to give you the opportunity to vote. Excuse me, if you would like more time to review the earlier stuff, if you think that this stuff is actually starting to kind of maybe a little bit make some kind of sense, and you've completely forgotten kinematics or whatever, then vote for more time for whole semester review. I will point out that the breakdown is roughly proportional to the number of weeks that we spent on each topic. So we're going to do 30% kinematics, 30% dynamics, 30% energy, 10% rotational crap. Yeah? Dynamics, I'm including spring force in there, even though I didn't teach it in those weeks. Because, I mean, come on, spring force belongs with force chapter. Okay? So, how should we do this? Google question A. I'm going to take a numerical average and decide from that how many days we should do review exercises. I mean, it's all sort of review. I'm not teaching new energy methods here. We're applying it and trying to make it make more sense. The question is, how many days do you want for full semester review? You may choose 1, 2, 3, or hell, I guess you could choose 4. I could start full semester review right now. I'm going to leave it up to you all. So again, you can vote 1, 2, 3, 4. This is how many days do you want for full semester review? My original plan, what's on the calendar, is to spend 1 day reviewing everything and 3 days on this material because it's the newest. But I'm going to take the average and give you guys what you need, what you want anyway. Hopefully it's what you need. You must put in a number because I'm going to use Excel's average function, Google Sheets' average function. If you type in text, it will be ignored. So again, type in a number, I guess, from 1 to 4. Oh, and people are typing in text. Well, it will be ignored. You will type in a number from 1 to 4, telling me the number of days you want for whole semester review. And the rest will be dedicated to just energy review. And the average is 2, 2, 2. Okay, so we will do this week will be energy. Monday and Wednesday will be energy. Next week will be everything review. And then finals. Any questions? Yeah, please. It's on the syllabus. It's on the Canvas. And also, by the way, for everybody's sake, for all of your college career, The instructors never set the times and dates for the thing. If you Google up ASU final exam schedule, you can get every exam for the rest of your life. Well, God willing, you'll graduate before then. There you go. You can find out when you get to fly for vacation in advance. Yeah, 6 months in advance. So you can always Google that. But yes, what'd you say? 2:30 on. You guys are at the Friday. Sorry. Yeah, I know it sucks. I'm sorry. Again, I don't set these. Don't blame me. 2:30 on Friday. I guess it's 3 Friday cents. Not Wednesday. Not during the normal class period. Yeah. I will not be here during the normal class period. I only have people email me, hey, where is class? A couple of times. Okay. Oh, and it's in this room. It is in this room. Instructors do sometimes change that, although I don't know why they would. Seems a terrible idea. Okay, so let's go ahead and get started. Energyland, I had a couple of proposals for questions that I think sound wonderful. Let's do them. One of them was, you guys may or may not have seen a trampoline question on Les Homework, where a trampoline jumpy boy, whatever, gymnast is bouncing, 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 and you were given information about just how much force is exerted by the trampoline when they're at this, that, and the other position. You're given what else are you given? You're given I believe you're given the max compression, and you're asked for the total height, or is it the other way around? Someone help me out. You're asked for the total height, or you're given the total height? You're asked for the total height, okay. You're given the displacement. So the model is the mental model, the picture you should have in thine head. Yeah, picture you should have in thine head is, and let's analyze this fully. Let's dive down and understand this. The picture you should have in your head when you hear about somebody bouncing on a trampoline is, what kind of force is it? What kind of energy? Spring energy. So come on, wake up, here boy, come on. I think I have to plug it in for a hot second. And that wakes the pencil up or something? I don't know. Ah, there we go. Okay, so here's the mental picture you should have. Here's the surface of a trampoline. And this is very not to scale. A jumper jumps on it. Boing. And then the jumper shoots up into the air. Boing. Whee! Very not to scale. Trampolines do not depress this much. You said you were given the max deflection and asked for the max height, right? Please. Oh, good. You got it up. Hi. Okay, so I just drew it, not according to. By the way, careful sketches, reading carefully what the problem says is muy importante. Okay, so I'm going to sketch this. Let me zoom in, make sure everyone can see big time. Big scale, big scale. Making it making an accurate sketch of the situation, making sure that you're reading it right. I just started assuming that they were asking for the height above the trampoline. That's not what she said. There we go. Thank you. Thank you. Also good for the numbers. Now you're given a graph, aren't you? What's the, let me take a quick peek at the graph. I already looked at it, but I just want to make sure. Okay, so it goes up to 2000 at 0.5. Okay. Danke dir. You are also given a graph of force on the vertical axis versus displacement on the horizontal axis. And it says that at 0.5 meters, The force exerted by the trampoline would be 2,000 newtons, okay? That's actually excess information. If you're clever, you can get around that. But anyway, what I'm going to ask you to do is I'm going to ask you, as always, to identify the former forms of energy in the system at various times, write the equation that they're equal, and win. Solve for whatever you want. In this case, we could solve for the velocity when he is passing through the equilibrium position, the flat level of the trampoline, and we could find the total displacement from the bottom to the top. Now, there is a seductive, wrong way to approach this. I'm going to warn you that when you are at your lowest point, and I've been at my lowest point many times, when you are at your lowest point, is the net force zero? No, you're bouncing. If the net force was zero, you wouldn't bounce back, right? Is the spring force equal to weight force? Google question B, is spring force equal to weight force? I just argued that that there must be a net force, that you must be accelerating. Google form B, is weight equal to spring force? There are only two forces on the gymnast. Ooh, many of you are breaking the law, breaking Newton's law. There are two forces on the gymnast. I'm telling you that the total force can't be zero. What can you conclude about those two forces? If the total isn't zero, can they be equal and opposite? No. Two things that do not add up to zero cannot have the same numerical value opposite directions. There must be a net force on the gymnast. There must be a bigger spring force up than weight force down. You can't say Kx equals mg. We did Kx equals mg a lot. A little. A couple of times. I will do an example later where Kx equals mg. But it doesn't make sense to say Kx equals mg here because they're not just standing on the trampoline at their lowest point. They are bouncing and they're in the middle of the bottom bounce. They are accelerating. There is a net force. If the forces were equal, they just stay there. They wouldn't bounce up. You see? Great. That's the big hint. Again, I challenge you to work on this for a minute. Find the forms of energy, write the equations, set them equal, profit. C is, see if you could find V at, what should I say? V at surface? V at surface of the trampoline. V surface seems reasonable to say. And D is find delta Y, as shown. I'm going to emphasize that 72 kilos. Work with your neighbor. You only learn by doing. I'll give hints in a minute. Give a solution in a minute. Mm-hmm. Remember, I'm taking points off for completely ignoring instructions. For these questions, do not write a paragraph. Do not write a sentence. Do not write words. Google question C, I am looking for a number. Google question D, I am looking for a number. What's your number? Do not tell me your phone number. Those are not the answer. If you wish, you can include meters per second and meters. But if you write me more than just a number and maybe a unit, you're gonna get counted off because you're not listening. Ready, set, resume. Two more minutes to have started wrestling with it. And I'm going to give you a round of hints. Then I'll solve it for realsies. Oh, so much better. Okay, a brief round of hints. Brief-ish. Round of hints. I'm going to give you another chance to solve it based on what I tell you. And then I'll give final solutions and after I give you another chance to solve it. At each time, this is how to solve any energy problem. At each time, we're going to identify what form or forms of energy do we got. We're going to plug into the appropriate formulas, half kx squared, mgh, half mv squared. If there's an external work done, force times displacement with a plus minus. That lets you create the change in total energy is equal to the external works. That's it every single time. Then we just solve for whatever we want. If I'm talking about the V at the surface, one of those times it better be that I'm analyzing better be at the surface. I only really have enough information. I don't know at the peak. So if I'm looking for V surface, I think I'm going to compare where I have information about at the bottom to at the surface. Hey, what other information did I provide to you, by the way? What else are you given? Well, I'm given a force versus displacement graph. What can you deduce from force and displacement? How are force and displacement related even with springs? What's the formula for spring force? Oh, this should be something you know. Kx, baby. Force, kx. Energy, half kx squared, okay? So if I've got a graph of force, F, and I've got the x is on the x-axis, how do I see spring constant? No. This is not where I just say it out loud. Let me challenge you. If I graph force on the vertical and position on the horizontal, how can I see from this graph, how can I deduce the spring constant? This is Google Form E. You may describe in words. Don't give me a full sentence, please. Don't tell me the number. Give me a few words describing where the spring constant is on a graph of force versus distance. Again, that's question E, not question D. Yay, lots of people. Okay, so the technique that I will use, as many people know, is to find how much force changes per change in x. That's the slope of the line. Slope is the rise over the run. Force over displacement. Force over displacement is the meaning of k. So what's k in this case? 4,000. 2,000 divided by 0.5, not 5, 0.5, is 4,000. So hey, I didn't ask for that explicitly, but that's a good thing to know for this problem. Oh, I should have prompted you for the units. Newtons per meter. Okay. So I know something about what's going on at the bottom. I know that I've got springification going on. I know I don't have motion going on, remember? When you're at your lowest point, you are not moving down and you are not moving up, right? Yeah? So your velocity is 0. You don't have kinetic energy. Are you comfortable? It was really challenging a lot of people last week. Okay, so you've got spring energy. You don't have motion energy. Do you have positional energy? The answer is correct, whatever you said. As long as you're internally consistent, pick a reference point, call that height equals 0. If you're internally consistent, every other part of the problem, you'll be done. I am going to choose the lowest point as my reference point because both of the other measurements described in the problem refer to relative to the lowest point. So I choose that is the line y equals 0. Do I have potential energy if I'm at y equals 0? What's mgy when y is 0? 0, right? So I could say my only form of energy at the lowest point is what kind? Hopefully you were listening and remember what I said multiple times a second ago. Okay, now I'm connecting this. If I want to know about V surface, I want to know about what happens when I am at the surface of the trampoline. Tell me, is there trampoline spring energy? Am I moving? Am I at y equals 0? I defined y equals 0 half a second ago to be here. You can choose, but you have to be internally consistent. If you call the lowest point y equals 0, this ain't y equals 0. So based on the choice that I made, I would say that I do have gravitational potential energy and I do have kinetic energy. Write down, and I'll just give the hint, there are no other forces doing work. It said assume no friction. All the energy goes into the other forms, so external work is 0. All you got to do to solve problem part C, to find the surface velocity, is impose no change in total energy. Write down the initial form, write down the final form, their difference is 0. I'm going to give you another chance to work on that. So this is, you may put, if you fix a wrong answer, put that answer back in C. You can change your answer for C. If you did not complete it, a third of the class didn't finish a first pass, put that in C. If you realize this technique works for every single problem, you should be able to apply it to part D as well. I'm going to give you another 3 minutes. Oh, don't write this down, memorize this. This only applies to one particular problem. It's the technique, baby. It's the technique. Here's what I just did verbally 2 minutes ago, 3 minutes ago. What form or forms of energy do we start with? We reasoned through. It is just elastic potential energy. What form or forms do we have at the surface? We have some kinetic and we have gravitational potential relative to the starting point. The change in energy is, well, I hinted there are no other forces doing work, so work external is zero. If change from final to initial is zero, final minus initial equals zero, then we plug in and algebra. I only don't know V. Well, hey, hold on a second. Height. What is H? What does that represent in the final gravitational potential energy term? What is that? What does it mean? You can't just don't alphabet soup physics. You got to know what it means. In this problem, what's H? Which height? You guys know? What do you think? Yes. And why do you think that? Correct. I stated that I'm choosing this as zero. Yeah. And how far above this have I gone is the increase in gravitational potential energy. So H is that 0.8 meters. Hey, what's the x in half kx squared mean? It's the amount the spring is compressed or extended. In this problem, what is that? 0.8 as well. Be careful. I have warned before. I will warn again. I'm going to warn now. If you treat physics as alphabet soup, you might think, oh, X, H, I've got two different letters. I don't know all this. Too many letters. You will miss the idea if you recognize what does this represent and ask yourself, yeah, but what's it mean? What am I talking about every time? You won't make mistakes like this. It is very much like if I'm teaching a public speaking class, they might tell, well, you don't have to tell people this in common knowledge because everybody knows it and applies it in common sense in person. If you meet someone named George, they say, hi, my name is George. Do not then call everybody that you meet George. He is George does not mean that every subsequent he is George. If this means George, you have to apply that and recognize that somebody later may point at the same person and recognize that the meaning of that is also George. If you interpret and think about meanings, you won't make mistakes. If you just look for alphabet soup, letter equals letter, what? You will be a very silly person at parties. That said, let's plug in numbers. 1/2 times 72 times unknown squared plus 72 times, what the hell, 9.8 times 0.8 minus 1/2 times, what do we find K is? Times 0.8 squared. Solve for V. Do you guys feel confident in your ability to solve for V in this equation? No. Let me give y'all a chance, and then I will show you how to arithmetic it out. I guess it's algebra. Give it a shot, and if you get a different value in C, you're allowed to amend that. $4,000, $4,000, $4,000. I said 5,000. Okay, here's my techniques to algebra. One is I've got a lot of numbers that I could just evaluate. Half of 72, 1/2 times 72, bam. 72 times 9.8 times 0.8, bam. I'm just going to round a bit. I'll keep a guard digit. I don't have 3 sig figs here, but whatever. 1/2 times 4,000 times 0.8 squared, 1280. And I can evaluate 564 minus 1280. Incidentally, I encourage you, if this is not a solid skill for you at this point, do it slowly and be able to justify every step that you take. Be sure of the steps. Math doesn't have to be a guessing game. You can reason about each step. Once you get to this point, there are many places where people die. Let me remind you of the fundamental idea of solving one variable equations in algebra. Screw PEMDAS. PEMDAS tells you how to evaluate. We're going to go backwards. PEMDAS tells us first exponent, then multiply, then subtract. Screw that. I'm going to undo the subtraction first. How do I undo a subtraction? I'm going to add to both sides. Yeah? Screw PEMDAS. I'm not going to take care of the square first. I'm going to get the 36 away. How do I get a 36 away? Do I subtract? No. Why do I divide? How is 36 attached to V? It's attached when I write 2x, I mean 2 times x. So I would divide both sides by 36. What's 716 over 36, somebody? Somebody have a calculator handy? 19 point what? 90.9, okay. And then at the end of the day, all right, I've got a square. How do I undo a square? I apply the reverse operation. Undo it, bam. Again, every single step comes from a logic standpoint. You don't have to guess. If you try to skip steps and you don't have your license yet, don't. Take it slower and you can always know what the right thing is to do. Screw PEMDAS to algebra things. Do you guys all know what PEMDAS is? Yeah? Okay. The different people use different acronyms. I just wanted to make sure you all heard of that. Okay, so that's Vmax, not to be confused with Remax, which is something entirely different. We are going to repeat the process for finding the max height. I'm going to say that our max energy, which we could get just by plugging in the previous one, our max energy is our total energy doesn't change. So our energy here is our total energy here is our total energy there. What form or forms do I have at the highest point of my motion? UG, UG. There's no spring compression. And if you're at max height, you're not moving up, you're not moving down, you're not moving at that instant. So at that time, I would say, well, let's see, 1/2 mg. And what h is this? Should I plug in 0.8? What h makes sense to use when I'm talking about at the peak position? Delta y makes sense to use because I've defined this as my 0. How high am I? How high am I, man? I'm delta y above. That's the unknown. I claim that that is equal to my max, uh, 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 my max, um, my max total energy, which is, if you plug things in, it's 1280 joules. Okay, I could plug in M, I could plug in G. And I think it might be smoothest to evaluate both sides, well, evaluate the left-hand side first. I get 353 delta Y's equals 1280. I hate having to use a calculator. Delta Y, I undo multiplication by division. Okay, again, I have so many students ask me, where'd that equation come from? Don't learn this. Don't memorize this. Make this. This is an application of our one and only equation. This is always true. That's down there now, is only sometimes true. If you know how to find an energy at some time, minus the energy at an earlier time, if you know how to find works done, you can make any equation for any problem and always get it right. It's the same process every single time. Please turn to your neighbor and I want you to discuss the technique here and how it applies. There are many steps to this, but there's very little depth. This might be a mile wide, but it's an inch deep. Please reflect on the process so that you see the forest for the trees here, mixing metaphors. 1 minute to discuss. Okay, I'm actually hearing a lot of on-topic chatter, which is great. Raise your hand high if you feel like another 2 minutes would benefit you're actually making sense and learning from this. Let me vote. I will give you another 2 minutes if... Okay, it was only a couple people, but there were people up there. I got to give another 1 minute and then we move on. Then I give you your next problem where we're going to do the same thing again. Do you have a question too? How high above this lowest point will it rise? 0.8 meters below the equilibrium.
Yeah.
If that's interpreted as the where it's balanced, then I screwed up. Wait, also, hold on a second, hold on a second. They're 400 steps from that says 2000. Okay, I did get K correct. Okay, what? It's not half MGY.
Shouldn't be there.
It's half MV squared. MGY. Did I include a half MG? Oh, my sweet baby Newton. Oh, thank you very much. I was running off on a tangent, and the mistake is in the very last. That was a check to see if you knew what was going on, and she's the only one who passed. Very good. Thank you. Gravitational potential energy is not half MGH, it's MGH. So what would this be? 706, which turns this into 1.8. Thank you again. Okay. Let me give a related problem that I made up and build up to it. Here's the problem I'm going to guide you through. You guys know those little spring scales at the supermarket, right? What happens if you drop bananas on a spring scale? Boing, right? Vibrates a little bit. We haven't talked enough about oscillations yet. Well, that's a subject for next semester, really. So I'm not going to talk about the oscillatory behavior. I just want to go from the moment the bananas set on the surface to where they're in balance. And what I'm going to imagine doing is I'm going to hold my hand under, supporting some of the weight of the bananas so that as the bananas lower, they don't overshoot the balance point. Does that make any sense? You got something coming down, and if you didn't have your hand, it would overshoot and vibrate around an equilibrium point. You're just lowering it down with your hand. And the challenge question is, can you discover how much work your hand must do in order for the bananas to come to come to the equilibrium point? Sorry, you did that? And it's all the same. It's all the same. It's all the same problem, just in different disguises. So I'm going to give you an initial state. Here's the initial state. Here is a spring scale. Oh my God, that's so much better than how I drew it before. Here's the spring scale initially. The instant before the Berniner touches the spring scale. The instant before it starts to compress. And what I said is if you let the thing just fall under its own weight, it would vibrate up and down the sinusoidally. We're not going to go there. Instead, you're going to put your hand out. That's your hand. And you're going to let this lower smoothly down to its equilibrium point, which is in the middle. Your challenge, so you got a medium spring. Your challenge is to discover how much work your hand does on the Bernerners as it allows this to lower. You need to assume, there is an assumption here you're making, that we're lowering it slowly. If you let it fall very quickly, or if you let it speed up, or if you slow it down differently, you're transforming energy into partially kinetic, partially doing work. I don't want to do that. Assume you're lowering at constant speed, so kinetic is never a changing factor, okay? What will I give you? Hey, what did I give before? 2 kilo bananas? Did I give the spring constant, or did I give... And that ended up being too big a jump, I think. I'm going to give the spring constant as 100. Okay. So we've got 2 kilo bananas, 2 kilograms of bananas, or manea, as my baby says. And the spring constant is, let's say, a nice 100 newtons per meter. Find work by the hand to bring Bernerners smoothly to their balance point. Hey, remember what I said earlier? Hopefully you remember everything I said earlier. Wouldn't that be nice? Uh, Professor's dream. Student's dream, perhaps. Oh, no. Think of all the terrible puns I make. Probably better that you don't remember everything I say. Now, what I was saying at the very beginning of doing all these problems is that in the previous problem, the bottommost position is not in equilibrium because the guy's bouncing on the trampoline. If you're in equilibrium, you'd just be sitting there. The hint is at this point where we're trying to lower the Bernerners to, there they are going to be kx and mg in balance, yeah? Hint, hint, hint. Give this a stab. I'll give you a hint, and then we'll take another stab. Try it in F. F, find the work. Just a number, not a sentence. Thanks again for catching that half. I was in a cold sweat. That for a reason. All right. I asked for work. What's the work formula? Force times displacement, right? I don't know the normal force of the hand. I don't know the displacement. I'm screwed. No, because you could use the same formula and the same techniques that we've been doing, as I've promised multiple times, to find the work done by the hand. The work done by the hand is the only external work, so it's equal to the change in energy. Find the initial energy, find the final energy. That change is the work done by the hand. To do this, as always, we must identify what form or forms do we start with? What form or forms do we end with? Well, what do we start with at the beginning of the problem? I think we have got something which is up and going down. I choose to define the equilibrium position as y equals 0. The lower position is y equals 0. My hint that I gave earlier is if you play with speed, you can get these answers to be different. I'm going to say we're lowering it smoothly and steadily and slowly. We're not going to have a big kinetic. We're going to do it so slowly that kinetic is ignorable. Okay? So, what form does that leave? UG. Oh, what form does that leave? I didn't rule out spring energy. I said that, of course, it starts up, so we're going to use an MGY. Great, we've got M, we've got G. Oh, we don't have Y. Hey, well, what's the second point, by the way? What's the second time? What form or forms do we have? Do we have potential energy now that we're down? Do we have gravitational potential energy? No. Do we have spring potential energy now that we're down? Yes. Is the spring compressed? Do we have motion energy? No. My hint was, again, do not consider motion energy. You can go as slow as you want. I choose to lower so slowly that half mv squared is ignorably small. Okay, so I can write down the mathematical sentence that the initial energy is just mg times however high we start out. The final mathematical, the expression for the final energy is just half k. However far we move, however far compress. Looks funny to say it h, but whatever, I'm going to use the same letter. And that the work done by the only force that's doing the work, the only force that's left, the hand, is the final minus the initial, 1/2 kh squared minus mgh. You know I gave you k, I gave you m, you know g. 1/2 is a constant that should be known to you, but we don't know h. Well, let's consider if we do know something about what is going on with the bananas at the equilibrium point. What was the hint I gave just before you started doing this? We're not vibrating. We're not going up and down. We're not accelerating. At the equilibrium point, equilibrium means no net force at that point. You could take your hand off it and it's just going to stay there. What forces act on the banana at that time? Spring up, weight down. Which one is bigger? If it's not accelerating, they have to be equal, right? If you had a net force, it would have to accelerate. When the total force is 0, when the acceleration is 0, up E equals down E. So if mg equals kx, oh, there's a way to find the compression. There's a way to find h. If you followed what I was doing, implement that, plugga, plugga, chugga, chugga, you're done. I'm going to give you guys another 2 minutes to try to implement that. One more time, if you weren't listening, impose the condition that at equilibrium, equilibrium means that if they're only the force of spring and weight, those must be in balance for it to be staying there. Mg has got to equal Kx. Okay, take 2. You may amend your answer for F. All right. What was the hint I said to find H? Mg equals Kh. Why does Mg equals Kh? Because I said that we're at equilibrium at the second time when we have compressed a distance h. So I'm going to impose that condition. The spring force upward is balancing the weight force downward. I can use that to find h. Now let's plug in numbers. H equals what's m? What I give you 2 kilos times what the hell? 10 for G divided by 100 for K. Oh, it's like I picked 100 for a reason. $20 centimeters, that's still too big. Whatever. Okay, so there's H. Now I can take this H and shove it back into the original expression. What is the change in total energy? 1/2 K H squared minus M, not half M, watching carefully now, H. This is equal to the work done by the hand. Please, again, do not memorize this expression for WH. This is true in this particular case. Look at the techniques. And I get -2 joules. Negative? Does it make sense, or did I screw something up? Does it make sense that the hand did negative work? Talk to your neighbor for a second. Did I screw things up again? Take a vote, even. Does it make sense? Here's the Google question. Put it on Google form. Question G. Did I screw up? Is that negative sign right or wrong? Is that negative sign right or wrong? Is Google question G. I want you to discuss why it's right or wrong. G, Henna, that's correct. Is the minus sign right? Or did I goof again? I am a goof, but did I make a goof? Okay, let's discuss it. Sign of work, where's that come from, baby? The angle between what and what? The force that we're talking about and the displacement of the object. So which force are we talking about here? There are lots of forces. Which force am I asking about? If I'm asking about the work done by the hand, don't tell me about some other force. I want to know the force that the hand exerts on it. Which way does your hand push on the banana scale? I am supporting part of it as it descends, right? I'm pushing up on it to keep it from falling faster. You exert an upward force. Which direction is its displacement? Angle between that is 180. Cos 180 is -1. That minus sign is correct. Okay. One more time, I will remind you to ignore this week's homework because it is worth negative points. And if you submit it, you will get negative points. I have put last week's homework extension and a reminder on Canvas for that one. I apologize for not putting the reminder on Canvas before. And finally, I love each and every one of you. Now get out of here.